Okay. Um, in this video, we will solve physics problems. And here's the first one. Okay, so we have a small particle. Sorry, I should say that this is from a book by Serway and Jewett. Okay, so this is from, I will write that in the comments actually, or the description of the video. A small particle of mass m is pulled to the top of a frictionless half cylinder of radius capital R by a cord that passes over the top of the cylinder, and it's illustrated in that figure. And part A, okay, so question A is if the particle moves at constant speed, show that F equals mg cosine theta. And we have a little bit of helping note here. If the particle moves at constant speed, the component of its acceleration tangent to the cylinder must be 0 at all times. And B, by directly integrating the work, F dot dr, find the work done in moving the particle at constant speed from the bottom to the top of the half cylinder. Okay, so let's do part A first. Sorry, I need a pen, pardon. Okay, so we're going to do part A. Maybe I'll make that a little thicker if I can. Yeah, okay. Let me try again. Yeah, I think that's nicer. So part A, okay, for part A, what I would do is first draw the so-called free body diagram, okay? That's how I will start. Free body diagram. Okay, and I'm going to draw the free body diagram of the object. I suppose I could draw it on the figure. I will not do that because that will mess up the figure, but I'm going to draw it while the particle is in this generic position. Okay, so this angle is theta, and the particle is in this particular position, because actually the point here, one point here is that as the particle is moving up the incline, the angle changes. So the direction of the forces, some of the forces also changes. Okay, so I emphasize that this is a generic drawing for a fixed but arbitrary theta. Okay, so let me indicate the particle with its mass, and here's the particle, and obviously one force acting on it is going to be gravity. Okay. There's if we look at it, well, it's being pulled by the cord, okay? And we assume the cord is an ideal cord in the sense that it transmits the force as tension, okay? So actually here, maybe in that direction, roughly in that direction, we have, you could say tension, but that tension is the transmitted force by which it's being pulled on at this end. Okay, and the third force acting is obvious. Is if I go back to here, and that would be the normal force, right? That's what keeps it on going in the cylinder, you know, the semicircular path dictated by the cylinder, and that force is this way. Okay, and now what we can do from a free body diagram, of course, is draw or assess equations of motion, right? But before you do that, you need a coordinate system, okay? And for this particular system, so basically this direction here is the direction that's tangent to the circle, okay? So I tried to draw a tangent line there, dashed line. I didn't entirely succeed, okay? So I just state this again. This here is a tangent line, and that's this line on my free body diagram. And what we want now is first specify a coordinate system. I'm really going step by step here. So if you get used to doing this on an exam, you can go faster, but I want to go step by step. So there's a coordinate system, and the most convenient coordinate system in this case would be this one, I think, okay? So the x direction is the tangent, the y direction is the radial direction, okay? And Now I'm going to clutter my free body diagram a little bit. So this is the free body diagram, okay? Maybe I'll draw it again so I don't clutter the free body diagram itself, but I want to actually introduce additional information in order to be able to write the equations of motion. Okay, so again here, that's basically my free body diagram, but what I want to actually emphasize is that we have a triangle here whose angle here is theta. That's given here. Okay. And now what do we know? First of all, okay, if I want to do the x direction, which is the tangential direction, but that's actually okay. Well, we have to look at this triangle. Well, in the x direction, if this downward direction is the positive direction, then we have a minus f plus not mg, but its component this way. Its component this way. Okay, and now this angle here is a 90-degree angle, and so is this one. This is theta. This is 90 minus theta. So, and since this angle is 90, this should be theta. Okay, and this is also 90 minus theta. But anyway, from this little analysis that this angle here is theta, we see that this component, which is what we need here, is actually it's the adjacent over hypotenuse. So if the hypotenuse is mg, this is cosine theta. Okay, and we are told that there's no acceleration tangent to the cylinder because the object is being pulled at constant velocity. Okay, so this has to be 0. There's no acceleration this way. Now, we're not going to need the other equation of motion, but I will just write the one in the y direction. The one in the y direction would be, well, n. And if that's the positive direction, that's the positive n. Then you would need the other component of gravity, minus mg sine theta. Okay, and you have an acceleration, the centripetal acceleration. So the radial acceleration in this case is always v squared over r. Actually, it would be minus if you wrote it in a vector form. Okay, so it's towards the origin, and we are assuming that this point here, or alternatively, this point here is the origin. Okay, but based on this, we can write that this is minus mv squared over, sorry, I wrote this with a small r, that's the radius. So this is a generic expression for any circle you want. For our particular circle, the radius is capital R, so we have to write it like this. Okay, but first of all, this answers the first question. Okay, F equals mg cosine theta. Okay, we could go and calculate the normal force and velocity, but we're not asked to do that. So I'll just state that the answer to the first question is done. F equals mg cosine theta. Okay, and I go now to the second question. So let's go to the second question. I go back here. By directly integrating W F dot dr, find the work done in moving the particle at constant speed from the bottom to the top of the half cylinder. Okay, so I need my half cylinder. Maybe I will solve this B question here. Okay, so let me draw some separation lines. Okay, we have a force which is in the so-called tangential direction, but we can actually think of this as a polar system. So this, we can use a polar coordinate system. Okay, we will use a polar coordinate system. Our work integral is F dot dr like this. And we know that the magnitude of F is given here. We just calculated it. And we also know that it's in the direction of the angle. Okay, so let me actually designate the angle. So let's say the polar coordinate system, I don't have much space, but I will write it here as r and theta. Okay, that's my polar coordinate system that I'm going to use. So if I want to write F in vector form, in the polar coordinate system, I can write it as cosine theta and the unit vector in the theta direction. In addition, so basically at any theta, it's pointing in the theta direction. Okay, so in a polar coordinate system, let me draw one here just to make sure everyone knows what I mean. A point is specified by r theta, and you have a unit vector in those two directions. Okay, so one unit vector is the one in which r is increasing while theta is kept fixed. So that would be a direction of the r unit vector. The theta unit vector is that one where r is kept fixed and theta is the only one that's increasing. Okay, so that's, and the point is that this coordinate system, it's an orthogonal coordinate system, meaning that the unit vectors are perpendicular to each other, thank heavens. But it's a more complicated coordinate system than the Cartesian one, where at any point, the unit vectors, which are normally actually in the Serway and Jewett, they are designated as ij. So that's the x unit vector, that's the y unit vector. At any point you are, they are actually the same. Okay, here if you went to this point, your r would be pointing this way and your theta would be pointing that way. Okay, so it's a little bit more complicated to use such a coordinate system, it sounds like, but your integral is much easier because your integral depends on theta. Okay, so f is mg cosine theta unit vector. What is your dr? Your dr actually is also an arc length, and it also points in the theta direction, which will make the overall problem easy. So your dr is always at a radius. So your dr is actually the length as you make a change in the angle by d theta. That's your dr. Okay, so your dr, but you're always at radius capital R. So your dr is actually r d theta unit vector. Okay, so you have two vectors, and now you can take their scalar product. But the nice thing about taking this scalar product is that if you write f dot dr, that's mg cosine theta r d theta, and you're going to have a theta scalar product theta, and that is 1. Okay, so that is 1. Okay, now we can do our integral because this is all we need as our integrand. Okay, so the work is the integral from 0 to pi over 2. Let me read that again because okay, that's from top to bottom. So here the angle is 0, here the angle is pi over 2. I think it's from, by direct integration, find the work done in moving the particle at constant speed from the bottom to the top of the half cylinder. Yes, so the bottom would be here, the top would be here. Okay, and here the angle is 0, and here the angle is pi over 2. So let's do it. So we can write here the f dot dr we just calculated, and this one we just forget about, mg cosine theta r d theta. Okay, so mgr comes out of the integral, 0 to pi over 2. And inside we are left with cosine theta d theta. And that gives us mgr. We integrate cosine theta, that gives us a sine theta. And the limits on that are 0 and pi over 2. So it gives us, because sine of pi over 2 is 1, and sine of 0 is 0, it gives us mgr. Okay, so that's the total work done. And now if you go back to and look at the problem a little bit, that seems quite sensible, right? Because you're doing work against gravity. The normal is there, but the normal is always perpendicular to the displacement. Okay, so the normal force is perpendicular to dr. So the normal does no work. Okay, so F only has to do work against gravity. Okay, and basically the work done is mgr, which is also equal to the change in potential, gravitational potential energy of the object as you bring it from the bottom to the top. Now, let me actually just look at one thing here, because actually, in principle, you could do one could do this problem in another way. One could actually, okay, so if I have my mg cosine theta, okay, force acting in this direction, I think this is the cleanest way to do it. But another way you could do it is to say that, well, just basically what we are saying is that F, so what I'm trying to say here is that you could do it in another coordinate system. In other words, you could always take the component of the force, which points in the at any angle, the force has a component in the direction of gravity. Okay, and you could do it that way too. So what you could do is to say W equals 0 to R F Y D Y. Okay, and basically,